Think about this for a moment. Every single thing you can see right now, the ceiling above you, the dim glow at the edge of the curtain, the faint outline of the room you are lying in, all of it exists because a colossal ball of nuclear fire has been burning 150 million kilometers away for the last 4.5 billion years. Now let me ask you something. What would happen if it simply stopped? Not dimmed, not cooled gradually over 1 billion years the way astronomers predicted eventually will, but vanished. Completely. Instantly. Right now, while you are listening to this, while your body is growing heavy and your breathing is beginning to slow, what would you notice first? Would there be a sound, a feeling? Would the air change? Would you know? And what would happen next? Not in 1 million years, not in some distant future that feels safely abstract, but in the next 8 minutes, the next 8 hours, the next 8 weeks. What would happen to the sky, to the oceans, to the animals sleeping in forests across the world, to the ground beneath every city, to the very chemistry of the air inside your lungs? Tonight on Learn When You Sleep, we are going to follow the disappearance of the sun all the way from the first fraction of a second to the final cold silence of deep time, through 100 scientific truths, each one stranger and more beautiful than the last, each one a step deeper into a journey your mind can take while your body completely lets go. You do not need to hold on to all of it. You do not need to remember the numbers or the names. You only need to breathe and listen and allow the science to wash over you like a slow and gentle tide. Let us begin. The light you see from the sun right now is already 8 minutes and 20 seconds old. This is the first and perhaps most quietly astonishing fact about the star at the center of our solar system, and it is the key that unlocks everything else about what would happen if the sun were to disappear. Light travels at approximately 299,792 kilometers per second, which is the fastest speed that anything in the known universe can achieve. And yet, even at that extraordinary velocity, crossing the 149.6 million kilometers between the sun and the Earth takes precisely 8 minutes and 20 seconds. This means that in the hypothetical scenario we are exploring tonight, if the sun were to vanish at this very moment, you would not know for 8 minutes and 20 seconds. The sky would still be lit. The warmth on any sunlit surface would still be radiating. Birds still navigating by light gradients would still be flying. Every solar-powered process on the surface of the planet would still be receiving energy. The universe would be hiding its secret for those 8 minutes, burning through the last photons that ever left that dying star, allowing the final gasps of ancient sunlight to complete their journey before the darkness arrived. There is something deeply human about that delay, a universe that gives you almost 9 minutes to simply not know what has already been lost. The moment the sun disappeared, the gravitational influence of its mass would also cease to propagate outward at exactly the speed of light. Gravity, according to Einstein's general theory of relativity, does not act instantaneously across distance. Changes in gravitational fields propagate as gravitational waves, rippling outward through the fabric of space-time at the same speed as light, meaning that the Earth would not feel the gravitational absence of the sun until the same 8 minutes and 20 seconds had elapsed. Before that moment arrived, Earth would continue orbiting a gravitational well that was no longer actually there, tracing the same curved path through space it had always traced, held in its familiar ellipse by a force that, in physical reality, had already vanished. This is one of the most counterintuitive consequences of modern physics, because our everyday instinct is to imagine gravity as an instantaneous connection, like a string pulled taut, but it is more like a wave moving through a medium, and that medium, space-time itself, takes time to transmit the news of what has changed. For those 8 minutes, Earth would be the last dancer still moving after the music had already stopped, completing its final graceful arc before the silence reached it and everything changed forever. When the last photon from the sun finally completed its journey and the light reaching Earth simply ceased, the transition from day to night across the sunlit hemisphere would happen at the speed of light itself, meaning it would be instantaneous from any single observer's perspective. There would be no gradual dimming, no orange twilight stretching across the horizon, no slow gathering of dusk. One moment the sky would be fully lit with solar radiation, and the next moment it would not. The transition would be so abrupt, so utterly unlike anything in human experience, that the visual cortex would likely struggle to process it as real, because every experience of darkness that a human brain has ever encoded has involved some kind of transition, some gradient of change, and this would offer none. People in the daylit hemisphere would experience what might be described as an instantaneous blindness, not because their eyes had failed, but because the source that had been feeding light into every surface and scattering it through every molecule of atmosphere had simply stopped. And there is no neurological framework in the human brain for that particular kind of sudden nothing. A darkness that arrives not like a door closing, but like a sentence ending mid. In the first seconds after the light ceased, the human eye would begin a process called dark adaptation, a cascade of photochemical and neural changes that would allow vision to shift from cone-dominated daylight perception to rod-dominated low-light sensitivity. This process happens every night as the sun sets, but it normally unfolds over approximately 20 to 30 minutes, with the most dramatic gains in sensitivity occurring in the first few minutes as rhodopsin, the photosensitive pigment in rod cells, regenerates from its bleached state. On a night when the sun has disappeared, the sky would not be completely dark, because the moon, if it happened to be above the horizon, would still be reflecting light, and the stars, billions of them, would remain, their ancient light already traveling toward Earth across the void. Observers in the former daytime hemisphere, their pupils dilating rapidly, their rod cells regenerating, would begin to perceive a sky unlike any they had ever seen, a sky with no gradual transition, a sky that went directly from full daylight to a star field of extraordinary density, a sky that would remind every human who looked at it in the most visceral possible way that the sun had always been the reason they could not see those stars before. The surface temperature of the Earth would begin to fall almost immediately after the solar radiation ceased, but the rate of that cooling would vary enormously depending on location and surface type. Bare rock and sand, which have low heat capacity and absorb and release energy quickly, would begin to cool within minutes. The great desert surfaces of the Sahara and the Arabian Peninsula, which routinely reach temperatures of 60 degrees Celsius or more, would begin radiating their stored heat back into the atmosphere and then into space with nothing to replenish it. Water, by contrast, has an extraordinarily high specific heat capacity, meaning it requires much more energy to change its temperature, and the surface layers of the world's oceans would cool much more slowly, over days and weeks rather than hours. This disparity between land and ocean cooling rates would immediately begin to affect atmospheric pressure patterns, altering the wind systems that distribute heat and moisture around the planet, creating pressure gradients that would generate unusual and perhaps violent weather patterns in the hours immediately following the sun's disappearance. As the atmosphere struggled to redistribute the uneven thermal energy remaining in the system, it had suddenly been cut off from replenishing the magnetosphere of the Earth. The invisible magnetic shield that deflects the constant stream of charged particles from the sun, known as the solar wind, would not instantly disappear when the sun did, but it would begin to change in a subtle and important way. The solar wind is a continuous flow of electrons and protons streaming outward from the sun at speeds between 400 and 800 kilometers per second. And it is the interaction between this wind and Earth's magnetic field that creates the familiar teardrop shape of the magnetosphere, compressed on the sunward side and stretched into a long tail on the opposite side. Without the solar wind pushing against it, Earth's magnetosphere would slowly relax into a more symmetrical shape over the hours and days following the disappearance of the sun, gradually expanding as the last particles of solar wind passed by. This change would have little immediate practical consequence for life, since the magnetosphere's primary protective function is against radiation from the sun itself, which would also be gone, but it would represent one of the first detectable geophysical changes recorded by the sensitive instruments that continuously monitor Earth's magnetic environment. The process of photosynthesis, which sustains virtually all complex life on Earth, would cease the instant solar radiation stopped reaching the planet. Photosynthesis is a light-dependent biochemical process occurring in the chloroplasts of plant cells, where chlorophyll and other pigment molecules absorb photons and use that energy to drive the conversion of carbon dioxide and water into glucose and oxygen. The light-dependent reactions of photosynthesis require a continuous input of photons to excite electrons in the photosystem complexes embedded in the thylakoid membranes. And without that input, the electron transport chain would stop. The synthesis of ATP and NADPH would halt, and the Calvin cycle, which uses those energy carriers to fix carbon, would come to a standstill within seconds. However, the plants themselves would not die instantly. They carry stores of glucose and starch that they have synthesized over their lifetimes, and cellular respiration, the reverse process by which they break down those stores to power their own metabolism, would continue for a considerable period. A large tree might sustain itself for weeks or even months on stored energy alone, but the clock would be running from that first lightless second onward. The aurora borealis and aurora australis, the shimmering curtains of light that appear at high latitudes, are caused by charged particles from the solar wind interacting with Earth's upper atmosphere, and they would not immediately vanish when the sun disappeared. The solar wind travels much more slowly than light, at between 400 and 800 kilometers per second, meaning that even after the sun ceased to exist, a continuous stream of previously emitted solar wind particles would still be flowing through the inner solar system for some time. The distance from the sun to Earth is about 150 million kilometers, and at the average solar wind speed of roughly 500 kilometers per second, the journey takes approximately 3 to 4 days. This means that the auroral displays would persist for several days after the disappearance, fed by the last exhaled breath of the dead star, painting the polar skies in greens and pinks and purples with the eerie beauty of a farewell that the star itself could not witness. People who happened to be watching the northern or southern lights in those first days would be seeing, In a very real sense, the ghost of the sun performing one final light show before the stage went permanently dark. The tidal forces that shape Earth's ocean patterns and even contribute to the slow wobble of the planet's rotation are generated primarily by the gravitational pull of the moon. But the sun contributes approximately 46% of the total tidal force experienced on Earth. The particularly dramatic high tides known as spring tides, which occur when the sun, Earth, and moon align during new and full moon phases, are a direct result of the sun's gravitational contribution combining with the moon's. Once the sun disappeared and its gravitational influence ceased to reach Earth, the tidal system would simplify dramatically, driven entirely by lunar gravity. The oceans would still experience tides, twice daily as they do now, but the amplitude of those tides would reduce significantly, and the extreme spring tides that coastal ecosystems have evolved around for hundreds of millions of years would cease. This change would begin exactly 8 minutes and 20 seconds after the sun vanished, when the gravitational news arrived, and it would ripple through coastal and marine ecosystems in ways both immediate and long-lasting, quietly rewriting the rhythmic pulse that the sea had kept for as long as life had been breathing beside it. The moon, which has no light source of its own and shines only by reflecting sunlight, would go completely dark within the same 8-minute and 20-second window as Earth's own illumination ended. Because the moon is slightly closer to the sun than the far side of Earth, and slightly further from the sun than the near side, the exact moment of its darkening would differ by fractions of a second depending on the moon's position in its orbit. But to any observer watching the sky, it would appear to vanish essentially simultaneously with the extinction of all direct solar illumination. The moon's loss of reflected light would remove what has historically been humanity's most important source of nighttime illumination, the light that has shaped agricultural calendars, navigational systems, religious festivals, and the poetry of every human civilization. Stars and planets would remain, and some planets closer to what had been the sun, like Venus, might still reflect some residual sunlight for a brief period depending on orbital positions. But the reliable silver glow of the full moon that has accompanied every human generation since the species first looked upward would be gone, replaced by a dark disk occluding the stars, a shadow where a mirror had been. Solar panels and photovoltaic systems worldwide would cease generating electricity within those same 8 minutes, their silicon cells no longer receiving the photons that had been exciting electrons across their semiconductor junctions. This would cause an immediate and catastrophic cascade failure in any electrical grid that relied significantly on solar generation, without sufficient storage or backup capacity. In regions like Southern Europe, California, and parts of China and Australia, where solar power contributes a substantial fraction of daytime electricity generation, the sudden loss would trigger automatic load balancing systems, switching demand to fossil fuel, nuclear, and hydroelectric backups. Grid operators would face an unprecedented event, not a gradual sunset that systems are designed to accommodate, but an instantaneous removal of capacity with no warning, no ramp-down period, and no recovery. Some regions with mature grid management systems might handle the initial shock, but the psychological and practical implications of knowing that the outage was permanent, that no amount of waiting would bring the solar generation back, would transform what began as a technical emergency into something much harder to manage with any ordinary protocol. The radio communications that modern civilization depends upon would be affected in complex ways by the disappearance of the sun. A significant portion of radio wave propagation on Earth depends on the ionosphere, a layer of the upper atmosphere extending from approximately 60 to 1,000 kilometers altitude, which is kept ionized primarily by solar ultraviolet radiation. Different layers of the ionosphere, labeled D, E, and F, have different densities of free electrons that reflect radio waves of different frequencies back toward Earth, enabling long-distance shortwave communication that bounces signals around the globe. The D layer, which is closest to the surface and primarily responsible for the absorption that weakens some signals during the day, would begin to recombine and disappear within minutes of solar radiation ceasing. The higher F layer, which enables the long-distance reflection of high-frequency radio waves, would persist for hours as it recombined more slowly. Over the course of days and weeks, all layers would gradually recombine, the ionosphere would largely collapse, and the radio landscape of the planet would be transformed, silencing communication pathways that had been available since the 1920s and that still serve as backup infrastructure in many parts of the world. The Van Allen radiation belts, two donut-shaped regions of high-energy charged particles trapped by Earth's magnetic field at distances of roughly 1,000 to 60,000 kilometers from the surface, receive their particle populations primarily from the solar wind and from cosmic ray interactions with the upper atmosphere. The outer belt is far more dynamic and variable than the inner belt, because it is continuously fed and depleted by interactions with solar activity, and without the solar wind to replenish it, the outer Van Allen belt would begin to thin over days and weeks as particles gradually leaked out or were lost to the atmosphere. The inner belt is more stable and fed largely by cosmic rays and the decay of neutrons, so it would persist for considerably longer. The practical significance for any hypothetical future space travelers would be real, because the Van Allen belts present a significant radiation hazard that mission planners must navigate, and a changing belt structure in the months following the sun's disappearance would alter the radiation environment of near-Earth space in ways that would need to be carefully characterized before any crewed mission ventured through that region. Plant life on the sunlit side of the Earth at the moment of the sun's disappearance would experience the cessation of photosynthesis as a sudden biochemical stillness, but the cellular machinery of plants would not stop all at once. Stomata, the tiny pores on leaf surfaces through which carbon dioxide enters and oxygen and water vapor exit, are typically open during daylight hours in response to light-sensitive signals, and they would begin to close within minutes of the light disappearing, guided by the same blue light-sensitive proteins that normally trigger their opening and closing in response to sunrise and sunset. This closing would reduce water loss and alter the gas exchange dynamics of the plant, representing a survival response that would buy the plant some additional time. The guard cells that control stomatal aperture are among the most rapidly responsive cells in the plant kingdom, capable of detecting and responding to light changes within minutes, and their rapid closure in the permanent darkness would be one of the first active biological responses to the loss of the sun, a small automated survival move made by millions of square kilometers of vegetation simultaneously. Each leaf quietly pulling its shutters closed against a night it had no way of knowing would never end. The solar radiation pressure, a tiny but real force exerted by photons striking surfaces, would cease along with all other electromagnetic output from the sun. This radiation pressure is so subtle that it is normally detectable only in the motion of spacecraft and tiny particles. But it has cumulative effects that engineers must account for in long-duration space missions, and it contributes to the gradual outward drift of solar sail spacecraft that are explicitly designed to use it for propulsion. For Earth itself, the effect of solar radiation pressure is negligible compared to gravitational forces, but for dust particles in the solar system, for the fine debris that creates the zodiacal light visible as a faint band across the night sky in very dark locations, the cessation of radiation pressure would subtly alter orbital dynamics over years and decades, allowing some of that dust to drift inward under gravity alone without the outward nudge of photon momentum that had previously helped maintain its distribution. The zodiacal light itself, which is sunlight scattered by interplanetary dust, would of course disappear along with sunlight, leaving the night sky incrementally darker and the inner solar system incrementally dustier over centuries to come. Any spacecraft currently in transit across the solar system would continue on their trajectories according to the laws of inertia and the gravitational influences of the remaining planetary bodies, but their solar power systems would fail instantly. The majority of spacecraft operating in the inner solar system, including the International Space Station and most Earth-orbiting satellites, rely on solar panels as their primary power source, and they would immediately begin drawing down whatever battery reserves they carried. The International Space Station, which generates approximately 84 to 120 kilowatts of power from its solar arrays, and carries limited battery reserves designed for eclipse periods of approximately 45 minutes during orbital night, would face an impossible situation within hours, as its batteries were depleted without any possibility of recharge. Distant spacecraft like the Voyager probes, which use nuclear radioisotope thermoelectric generators rather than solar panels, would be unaffected by the loss of sunlight in terms of power generation, and would continue transmitting their signals into the void, tiny voices, still calling out from the dark edge of the solar system, long after every solar-powered device in the inner solar system had gone silent. The color of the sky in the minutes immediately following the loss of sunlight would be a matter of extraordinary scientific interest if there were instruments positioned to record it. Under normal conditions, the sky is blue because the atmosphere scatters shorter wavelengths of light more efficiently than longer ones, a phenomenon known as Rayleigh scattering, which causes violet and blue light to scatter in all directions while red and orange pass through more directly. At sunset, the longer path length through the atmosphere shifts the apparent color toward red and orange. In the instant when solar radiation ceased, the scattering would also cease, and the sky would lose its blue color instantly across the entire daytime hemisphere, transitioning immediately from the familiar deep blue of a clear day to an absolute, sourceless black populated only by the light of stars and planets. There would be no color in that sky because color, in this context, is not a property of the sky itself, but of the interaction between sunlight and atmospheric molecules. And without the sunlight, the interaction is simply over, leaving a darkness that is technically identical to the darkness of space just kilometers above, a darkness that the thin shell of atmosphere can no longer paint blue. Migratory birds that use the position of the sun as one of their primary navigational compasses would experience immediate disorientation if they happened to be in flight at the moment of the sun's disappearance. Many bird species possess multiple redundant navigational systems, including sensitivity to Earth's magnetic field, the ability to orient by star patterns, and olfactory mapping, so the sudden loss of solar orientation would not necessarily be fatal for all individuals. However, species that rely heavily on a time-compensated sun compass, which uses an internal circadian clock to account for the sun's changing position throughout the day, would lose one of their most precise navigational tools instantly. The disorientation would be immediate and severe for birds mid-migration, particularly those over featureless terrain like open ocean, where other reference points are scarce. The simultaneous activation of whatever alternative navigational strategies these birds possessed would create an unprecedented natural experiment in avian cognition, a species-wide moment of sudden recalculation, as millions of individuals in the midst of journeys they had made before suddenly found themselves navigating by starlight instead of sunlight for the first time in the history of their kind. The gravitational release that Earth would experience 8 minutes and 20 seconds after the sun's disappearance would not be a violent event in any mechanical sense. Earth would not lurch or shudder. There would be no earthquake, no sudden tilting of the axis. The change would be mathematically precise and physically smooth. Earth, moving at approximately 29.78 kilometers per second in its orbit, would simply cease to follow its curved path and would instead continue in a straight line, a tangent to its former orbit, heading outward into the solar system in whatever direction its velocity happened to be pointing at that exact moment. This is precisely what Newton's first law predicts, and the direction of that straight line would depend entirely on where Earth was in its orbit at the moment the gravitational constraint was removed. Earth would not fall, it would fly, moving in a perfectly straight line through a solar system that was already becoming darker and colder, carrying with it its moon, its atmosphere, its oceans, its forests, and all the sleeping creatures on its surface, heading toward nothing in particular at nearly 30 kilometers every second, which is both very fast and, on the scale of interstellar distances, heartbreakingly slow. The first human beings to understand what had happened would most likely be astronomers and solar physicists monitoring the sun in real time through dedicated observatories. Facilities like NASA's Solar Dynamics Observatory, which continuously images the sun in multiple wavelengths, and ground-based observatories using coronagraphs and spectrometers to study solar activity, would record the cessation of all solar emissions simultaneously, and the data would be unambiguous and unprecedented. The instruments would record a flat line where there had always been a continuous signal, a silence in every wavelength simultaneously, and the scientists watching those screens would face a moment of profound cognitive dissonance, checking their instruments, checking their connections, calling colleagues, before the evidence became impossible to interpret as anything other than what it was. In the 8 minutes before the light reached Earth and went dark, these scientists would have data that no human being had ever held, the knowledge that the sun was gone before anyone else could possibly know. A window of 8 minutes in which the most important news in the history of our species existed only in data feeds, and the minds of a handful of stunned researchers staring at flat lines on glowing monitors in a world that still looked completely normal outside their windows. And so the first 20 facts of this journey have carried you from the speed of light to the last photon, from the stillness of photosynthesis to the straightening path of a planet released from its orbit. And already, the science has asked you to feel something that no simple fact can fully contain: the strange tenderness of a universe that gives you almost 9 minutes to not know what you have lost. Let these details begin to loosen their grip on you now. You do not need to hold the numbers. You do not need to keep the names of layers and particles and equations in the front of your mind. Let them drift back, like stars receding from a moving ship, still present, still real, but no longer demanding to be grasped. Your breathing is slower now, and the details are becoming softer, and there is more space between each thought. The next part of our journey will take us deeper into the hours and days that follow, into the slow transformation of ocean and air and sky. But for now, simply rest in the quiet weight of what you have already heard, and let your body sink a little further into wherever you are. The science will wait for you. The atmosphere of Earth would begin losing heat from its uppermost layers almost immediately after the sun disappeared, because the stratosphere and mesosphere, which are directly heated by the absorption of solar ultraviolet radiation, would start cooling from the top down, while the troposphere, the lowest layer where weather occurs and where most of the planet's heat is stored, would cool more slowly from below. The stratosphere normally maintains a temperature inversion that traps warmer air above cooler air, a structure that is entirely dependent on the absorption of solar ultraviolet radiation by ozone molecules. Without that energy input, the temperature inversion would begin to weaken within hours, and the stratosphere would begin to cool toward the temperatures of the mesosphere above it. This destabilization of the vertical temperature structure of the atmosphere would have cascading consequences for large-scale wind patterns, because the jet streams that circle the planet at high altitudes and drive the movement of weather systems are maintained in part by the temperature contrast between the tropical stratosphere and the polar stratosphere, a contrast that is itself driven by differential solar heating. As that contrast weakened and the stratosphere cooled uniformly, the jet streams would slow and meander unpredictably, disrupting the weather patterns that billions of people and ecosystems depend upon in ways that would become apparent within the first day. Within the first few hours after the sun's disappearance, the surface temperature of the Earth would begin a measurable and accelerating decline. The average surface temperature of the planet is approximately 15 degrees Celsius, maintained by a combination of solar input, the greenhouse effect of the atmosphere, and the internal heat of the planet itself. Solar radiation accounts for the vast majority of that energy budget, and without it, the planet would radiate its stored heat into space as infrared radiation, with nothing incoming to balance the loss. Climate scientists have modeled this scenario with reasonable precision, and the consensus is that within the first week, average global surface temperatures would fall to approximately -18 degrees Celsius, the approximate temperature the planet would maintain if it had no greenhouse gases at all, and then continue falling further as the atmosphere itself began to change. The rate of cooling would not be uniform, because the oceans, with their enormous thermal mass, would act as a slow-release heat reservoir, buffering coastal regions against the most rapid temperature drops, while inland continental areas, particularly at high latitudes, would experience catastrophic cold within days. A person standing in the middle of a large continent in those first hours would feel a cold arriving not like the chill of an autumn evening, but like a slow, unstoppable wall, a cold with no morning on the other side. The ozone layer, which occupies the stratosphere at altitudes between approximately 15 and 35 kilometers, and is responsible for absorbing the majority of the sun's ultraviolet radiation before it reaches the surface, is not a static shield, but a dynamic chemical system that is continuously created and destroyed by photochemical reactions driven by solar ultraviolet radiation itself. The primary mechanism of ozone creation involves ultraviolet light breaking apart molecular oxygen into individual oxygen atoms, which then combine with other oxygen molecules to form ozone. Without the ultraviolet radiation that drives this creation process, ozone would continue to be destroyed by its normal chemical reactions with nitrogen oxides, chlorine compounds, and other atmospheric chemicals, but would not be replenished. Over the course of weeks and months, the ozone layer would thin and eventually disappear, though in the absence of sunlight this would be largely irrelevant for life at the surface, since the ultraviolet radiation the ozone layer protected against would itself be gone. The disappearance of the ozone layer would nonetheless represent a profound and irreversible transformation of a planetary structure that had taken billions of years to build, a protective layer that had made the colonization of land by life possible, quietly dissolving in the dark like a guardian whose ward no longer needed guarding. The world's cloud cover would undergo dramatic changes in the hours and days following the sun's disappearance, driven by the collapse of the convective processes that normally generate clouds. Most of the clouds we see in the troposphere form because solar heating of the surface causes warm, moist air to rise, cool, and condense into water droplets or ice crystals. Without solar heating, the primary engine of convection would shut down, and the great towering cumulonimbus clouds of the tropics, the sprawling stratus layers of the mid-latitudes, and the delicate cirrus wisps of the upper troposphere would gradually dissipate as the thermodynamic conditions that created them ceased to operate. However, this process would not happen immediately, because there is still enormous latent heat stored in the oceans and in the lower atmosphere, and evaporation from relatively warm ocean surfaces would continue to generate moisture that could condense into low clouds for days or even weeks. The cloud cover during this transitional period would be thick and strange, a planet wrapped in clouds generated not by a living solar system, but by the dying thermal momentum of one, the atmosphere exhaling its last warm, breathless clouds that would have no sun to backlight them, hovering in permanent darkness over a cooling world. Ocean circulation, one of the most important heat distribution systems on the planet, would begin to respond to the loss of solar energy within the first day, though the full implications of these changes would take years to manifest. The global ocean circulation, often called the thermohaline circulation, or the ocean conveyor belt, is driven by differences in water temperature and salinity that create density gradients, causing denser water to sink and less dense water to rise in a planet-spanning current system. Solar energy plays a critical role in this system by heating surface waters at the equator and driving evaporation that concentrates salt and increases density. As surface waters began to cool uniformly in the absence of solar heating, the temperature gradients that drive the major current systems, including the Gulf Stream that moderates the climate of northwestern Europe, would weaken. The North Atlantic Deep Water Formation, which is one of the primary engines of the global conveyor belt and involves dense, cold, salty water sinking near Greenland and Iceland, would be disrupted as surface water temperatures fell toward freezing everywhere simultaneously, removing the thermal and density contrasts that the system depends upon. The ocean, which had circulated for billions of years, would begin a very slow process of becoming still, its great currents fading like the last movement of a clock that no one would wind again. Ice formation on the surface of the oceans would begin within the first day or two at polar latitudes, where temperatures were already near freezing, and would spread toward the equator with terrifying speed relative to any historical rate of ice formation. Sea ice normally forms when ocean surface temperatures fall below approximately -1.8 degrees Celsius, the freezing point of seawater, and in the Arctic and Antarctic, this happens seasonally in response to the reduced solar angle of winter. Without any solar input, and with the atmosphere cooling rapidly, the polar oceans would freeze within hours to days, and the ice front would advance equatorward at a rate that would be visible on satellite imagery, if any satellites had power to transmit it. The formation of sea ice would have an important feedback effect on the rate of cooling, because ice has a much higher albedo than liquid water, meaning it reflects more incoming radiation. But in this scenario, there is no incoming radiation to reflect, so the albedo feedback would be irrelevant. Instead, sea ice would act as an insulating lid on the ocean, slowing the rate at which the ocean lost heat to the atmosphere, paradoxically preserving some of the ocean's thermal mass beneath a frozen ceiling, while the world above it grew ever colder. The water cycle, the continuous movement of water between the surface, atmosphere, and back again through evaporation, condensation, precipitation, and runoff, is powered almost entirely by solar energy, and its disruption in the days following the sun's disappearance would be among the most consequential changes to the Earth system. Evaporation from the ocean surface would continue for a time, driven by the residual warmth of ocean waters that were still relatively warm compared to the atmosphere above them. But as the temperature difference between water and air diminished, evaporation rates would fall sharply. Precipitation would also change dramatically, because the convective updrafts that lift moisture high enough to form rain and snow would weaken as surface heating ceased, and instead precipitation would tend to occur as the moisture already in the atmosphere condensed and fell in a more uniform, drizzling fashion. Rivers and lakes would continue to flow and fill from precipitation and groundwater for a time, but as temperatures fell below freezing across much of the land's surface, rivers would begin to freeze from their banks inward, and the great river systems of the world would be silenced one by one, their voices stilled under layers of ice that would grow thicker with each passing week. The global wind systems, which distribute heat and moisture across the planet and moderate the climates of every region on Earth, are fundamentally driven by the differential heating of the surface by the sun, with warm air rising at the equator and flowing toward the poles while cold air flows back toward the equator at the surface, creating the trade winds, the westerlies, and the polar easterlies. Without solar heating, these large-scale circulation patterns would begin to break down within days. The intertropical convergence zone, The equatorial band, where trade winds from both hemispheres converge and rise, would weaken and eventually disappear as the equatorial temperature advantage over polar regions faded. The Hadley cells, the enormous atmospheric circulation loops that define the tropical and subtropical climate zones, would collapse. The weather patterns that billions of humans have built their civilizations around, the monsoons of Asia and Africa, the trade winds that made transoceanic navigation possible, the reliable westerlies of the mid-latitudes, would all gradually slow and become chaotic as the temperature gradients that drove them flattened out in the universal cooling, leaving a strangely still atmosphere over a darkening world. The deep ocean, which holds an enormous quantity of heat absorbed from the sun over millions of years, would not cool at anything like the rate of the surface, and this thermal inertia would play a crucial role in moderating the speed of the global temperature decline in the weeks following the sun's disappearance. The average temperature of the deep ocean, below a depth of about 2,000 meters, is approximately 2 to 4 degrees Celsius regardless of surface conditions, because deep water forms primarily at the cold poles and sinks to the bottom, where it circulates very slowly over centuries and millennia. This enormous reservoir of thermal energy, representing the integrated solar heating of the ocean over thousands of years, would continue to release heat slowly through conduction to the layers above it and through the ocean floor to the seafloor environment. Hydrothermal vents on the ocean floor, powered by the internal heat of the Earth rather than by the sun, would continue to operate, maintaining small warm oases in the otherwise cooling abyss, tiny independent thermal systems that had existed since before the first photosynthetic organism ever lived, warm in their own ancient way, entirely indifferent to the loss of a star they had never seen. The behavior of the atmosphere with respect to carbon dioxide would change in important ways as global temperatures fell, because the solubility of gases in water increases as temperature decreases, meaning that colder oceans would absorb carbon dioxide from the atmosphere more efficiently. Carbon dioxide is a greenhouse gas that traps infrared radiation and contributes to the warming of the lower atmosphere, and its atmospheric concentration would begin to fall as the cooling oceans absorbed more of it, which would accelerate the rate of cooling in a feedback loop, lower temperatures leading to more carbon dioxide absorption, leading to less greenhouse warming, leading to lower temperatures. This negative feedback on atmospheric carbon dioxide would be the reverse of what climate scientists model as a warming scenario. But in this context, it would contribute to the increasing pace of the global temperature decline, the atmosphere progressively losing one of its main insulating blankets as the cold tightened its grip. Eventually, as temperatures fell far enough, carbon dioxide would begin to freeze out of the atmosphere entirely at the poles, depositing as dry ice on the surface, further reducing the greenhouse effect and accelerating the cooling in a runaway process that would continue until very little carbon dioxide remained in the gaseous atmosphere above a frozen world. Freshwater lakes across the temperate regions of the world would begin to freeze from the surface downward in the days following the sun's disappearance, a process that would unfold slightly differently from ocean freezing, because freshwater has its maximum density at 4 degrees Celsius, rather than at its freezing point of 0 degrees Celsius. As a lake cools, the water at the surface becomes denser and sinks until the entire water column reaches 4 degrees, after which further cooling of the surface water makes it less dense, so it stays at the top and freezes. This means that even under extreme cold, a lake's bottom water remains at 4 degrees Celsius beneath the ice, insulated from the air above, and any organisms capable of surviving at that temperature could potentially persist for a very long time in this liquid zone beneath the ice. Fish that have evolved to survive cold winters under ice, invertebrates and microbial communities, would find themselves in an environment that was dark and cold but still liquid, still habitable in a minimal sense, carrying on in their ancient cold-adapted ways beneath a ceiling of ice that was growing thicker by the day, unaware and unconcerned with the cosmic event that had produced their new ceiling. The behavior of gases in the atmosphere would be affected not only by temperature, but by the removal of the photochemical processes that maintain the chemical composition of the lower atmosphere. Ozone in the troposphere, which is distinct from the protective stratospheric ozone layer, and is itself a pollutant produced primarily by the interaction of sunlight with nitrogen oxides and volatile organic compounds, would cease to form without sunlight. Many of the reactive chemical species that cycle through the lower atmosphere, including the hydroxyl radical, which is sometimes called the detergent of the atmosphere because it reacts with and removes a wide range of pollutant gases, are produced by photochemical reactions and would cease to be replenished without solar ultraviolet radiation. The chemistry of the lower atmosphere would gradually shift toward a more reducing, less oxidizing state as these reactive oxidants were consumed and not replaced, changing the way that natural emissions from vegetation and the ocean were processed in the air, and altering the lifetime of various trace gases in ways that would affect air quality and atmospheric chemistry for years to come. The behavior of nocturnal animals, creatures that evolved specifically to function in the absence of sunlight, and that navigate, hunt, and communicate in darkness, would be less immediately disrupted by the loss of the sun than diurnal animals, but they too would eventually face profound challenges. Bats, for instance, navigate primarily by echolocation and hunt insects that are themselves most active in warm, humid air, conditions that would disappear within days as temperatures plummeted. Owls, which hunt by a combination of exceptional night vision and acute hearing, would initially be advantaged in a world that was now perpetually dark, but the prey animals they depend upon would be dying or retreating into dormancy as the cold arrived, removing the food supply regardless of the hunter's sensory capabilities. Deep-sea creatures that have never been exposed to sunlight and live in permanent darkness, sustained by chemosynthesis or by organic material sinking from above, would find their world relatively unchanged in the immediate aftermath, though the cessation of organic material raining down from the surface ecosystem that was dependent on photosynthesis would eventually reach them even in the deepest trenches, cutting off the slow nutritional link between the sunlit surface and the permanent dark below. Precipitation patterns would shift in strange and counterintuitive ways during the first weeks after the sun's disappearance. While the general expectation would be that a cooling world would produce less evaporation and therefore less precipitation, the dynamics of the transition period would create local regions of intense snowfall as the moisture already present in the atmosphere condensed and fell on surfaces that were rapidly cooling below freezing. Areas that are normally too warm for snow could receive heavy snowfall as temperatures dropped suddenly below zero, while regions that typically receive significant rainfall would find that precipitation falling as snow rather than rain, accumulating rather than draining away, beginning to build the snowpack that would eventually cover much of the continental surface. Coastal regions, where the relatively warm ocean surface would continue evaporating moisture into the overlying atmosphere for weeks, could experience particularly heavy snowfall as that oceanic moisture encountered the rapidly cooling air over land, depositing significant snow accumulation in a short period, and beginning the process by which sea ice and land ice would eventually merge into a continuous frozen surface, extending from the coast inward across the continents. The electromagnetic spectrum of light reaching Earth from space would change completely in the days following the sun's disappearance. During normal times, the majority of electromagnetic radiation arriving at Earth is solar in origin, spanning from radio waves through visible light to X-rays and gamma rays, with the peak of the solar spectrum falling in the visible range. Without the sun, the electromagnetic environment at Earth would consist of the cosmic microwave background radiation left over from the Big Bang, the radio emissions of pulsars and other exotic objects, the X-ray glow of distant galaxy clusters, the infrared radiation of warm cosmic dust, and the starlight of hundreds of billions of stars across the galaxy, each contributing an infinitesimally small amount of light at Earth's location. The total light reaching Earth from all the stars in the sky combined is roughly 400,000 times less than the light provided by the full moon, and the full moon reflects sunlight that itself originates at the sun. So in the new sunless darkness, the collective light of the entire galaxy would provide less illumination than a cloudy night currently does. A darkness so deep and comprehensive that it would take human eyes adapted to the very darkest natural environments they have ever known, and make even those environments seem bright by comparison. The behavior of the world's great river systems in the days and weeks following the sun's disappearance would be shaped by a combination of freezing temperatures, reduced precipitation, and the cessation of the snowmelt that normally contributes to river flow in spring and summer. Rivers in tropical regions, fed by the convective rainfall of the intertropical convergence zone, would see their inputs dry up almost immediately as the atmospheric dynamics that generated equatorial rainfall collapsed. Rivers in temperate regions fed by glaciers and snowpack, which normally receive meltwater during warmer months, would continue flowing for a time from the residual thermal mass of the ice. But as temperatures fell uniformly below freezing, even this source would disappear. The rivers themselves, flowing over surfaces that were rapidly cooling toward and below freezing, would begin to ice over first at their banks and in their shallow sections, the ice advancing inward across the channel as temperatures fell, until even the fastest-moving rivers were captured and stilled beneath ice. The Amazon, the Nile, the Yangtze, the Mississippi, all the great arteries of the continents would fall silent one by one, their water locked first into ice and then into a growing continental glacier, the rivers of the earth becoming the bones of a frozen world. The atmospheric pressure patterns of the planet would undergo fundamental restructuring in the weeks following the sun's disappearance, as the thermal contrasts that maintain the planet's pressure systems faded away. The high-pressure systems that dominate subtropical regions and create the world's deserts are maintained by the descending air of the Hadley circulation, which is itself driven by solar heating at the equator. Low-pressure systems at higher latitudes are maintained by the temperature contrast between warm tropical air and cold polar air, a contrast that drives the development of cyclones and frontal systems. As the global temperature became more uniform, these pressure contrasts would diminish, and with them the synoptic scale weather systems that generate most of the world's significant weather events. Hurricanes, which require warm ocean surface temperatures of at least 26 degrees Celsius to form and maintain themselves, would rapidly weaken and dissipate as ocean surface temperatures fell in the first weeks. Extratropical cyclones would also weaken as the thermal gradients that feed them faded. The atmosphere of a post-solar Earth, after the initial chaotic transition period, would settle into a quieter, more uniform state, cold and still. A world where weather as we know it had been replaced by something more like the slow, quiet atmospheric chemistry of a dead planet. The behavior of bacteria and other microorganisms in the soil would initially be relatively unaffected by the loss of sunlight, because most soil bacteria are not photosynthetic and derive their energy from chemical reactions involving organic matter in the soil. However, the rapidly falling temperatures would have profound effects on microbial activity, because most microbial metabolic processes slow dramatically or cease entirely at low temperatures. The Q10 temperature coefficient, which describes how much a biological rate changes with a 10 degrees Celsius temperature increase, means that for every 10-degree temperature drop, metabolic rates roughly halve. As soil temperatures fell from typical values of 10 to 20 degrees Celsius toward freezing and below, bacterial decomposition rates, which play a crucial role in releasing nutrients back into the soil for plant uptake, would slow dramatically, locking up organic matter and nutrients in forms that plants could not access even if they had survived to try. The great underground ecosystem that underlies all terrestrial life, the billions of organisms per gram of topsoil that recycle carbon and nitrogen and phosphorus through the biosphere, would be gradually quieted by the cold, not killed immediately but slowed to a near standstill. A biological pause button pressed on a system that had been running continuously since the first life appeared on Earth over 3.5 billion years ago. The world's glaciers and ice sheets, which currently hold approximately 69% of all freshwater on Earth, would of course stop melting entirely and would instead begin to grow as the planet cooled and precipitation fell as snow. The Greenland and Antarctic ice sheets, which together hold enough water to raise sea levels by approximately 65 meters if they were to melt entirely, would see their surfaces begin to accumulate new snow almost immediately as temperatures fell below zero across their already cold elevations. The mountain glaciers of the Alps, the Himalayas, the Andes, and the Rockies, many of which have been retreating for decades due to rising temperatures, would suddenly reverse and begin to advance as fresh snow accumulated on their surfaces without any summer melt to remove it. Over weeks and months, these glaciers would thicken and spread, their fronts advancing down their valleys at speeds that would be noticeable over the course of a human lifetime, covering roads and villages and agricultural land that had been glacier-free for decades or centuries, the ice reclaiming territory it had surrendered during warmer times, indifferent to the artifacts of civilization it was burying, patient in the way that ice has always been patient, moving slowly in the dark toward a world it would eventually cover entirely. Now let the second part of this journey rest gently in your mind. The oceans are cooling, the winds are fading, the rivers are going quiet under their first layers of ice. These are large and slow processes, and your mind does not need to hold the pace of them. Let the atmosphere settle around you as you breathe. Let the temperature gradients flatten out the way your body is flattening into rest. Let the chemistry of the cooling air become something you simply feel rather than follow. There is no urgency in the science we are exploring tonight, only a deep and patient unfolding, one layer at a time, 1 degree at a time. The next part of our journey will take us weeks into the darkness, into the world of living things responding and adapting and persisting, and you will hear it all from somewhere warm and still. Let your thoughts drift a little further out now, the way sea ice drifts slowly, without effort, covering what was once open water with something quiet and white and undisturbed. The circadian rhythms of virtually every living organism on Earth, from the simplest bacterium to the most complex mammal, are entrained by the daily cycle of light and dark produced by Earth's rotation relative to the Sun. And the permanent absence of sunlight would represent the most profound disruption to biological timekeeping in the history of life on this planet. Circadian clocks are molecular feedback loops in which certain proteins accumulate during one phase of the cycle and inhibit their own production during another phase, creating an approximately 24-hour oscillation that is synchronized or entrained by environmental cues called Zeitgebers, from the German word meaning time givers, the most powerful of which is light. In humans, light detected by specialized photosensitive retinal ganglion cells containing melanopsin is transmitted to the suprachiasmatic nucleus in the hypothalamus, the master circadian pacemaker, which then coordinates the clocks of every cell in the body. Without light as a Zeitgeber, the circadian clocks of all organisms would continue to run on their intrinsic periods, which are close to but not exactly 24 hours, and they would gradually drift out of synchrony with the external world, with each other, and potentially with the clocks of other organs within the same body. Within weeks, the biological timekeeping of every living thing on Earth would be running free, untethered from the celestial rhythm that had wound it every morning for billions of years. Trees, which are among the longest-lived and most structurally complex photosynthetic organisms on Earth, would respond to the permanent darkness in ways that reflect both their remarkable resilience and their ultimate dependence on solar energy. Many tree species have evolved sophisticated mechanisms for surviving long winters without light or with greatly reduced light, entering a state of dormancy in which metabolic activity drops dramatically, water uptake ceases, leaves are shed to reduce water loss and structural load, and the tree essentially pauses until conditions improve. Deciduous trees in temperate regions, which lose their leaves every autumn and regrow them every spring, would enter what appeared to be a normal dormancy state in response to the sudden darkness, drawing on this ancient seasonal response protocol even though the stimulus was unprecedented in its completeness and its permanence. Evergreen trees, which retain their leaves year-round, would continue photosynthesizing at very low rates in any ambient starlight or artificial light that reached them, burning through their stored reserves slowly. The very largest trees, ancient individuals with decades of stored carbohydrate reserves, might remain technically alive in a dormant state for years, their metabolism reduced to a bare minimum, waiting in the dark for a spring that would never arrive, their rings recording the final winter as a band of compressed cells that future geologists, if there were any, would identify as the moment the world changed. The mycorrhizal networks that connect the root systems of trees and other plants in a vast underground web of fungal filaments, sometimes called the wood wide web, because of the way they facilitate communication and resource sharing between plants, would persist for a considerable time after the plants themselves began to die. Fungi are not photosynthetic and derive their energy by breaking down organic matter or by forming symbiotic relationships with photosynthetic organisms, and the mycorrhizal fungi associated with tree roots would initially continue to function as their tree partners drew down their stored reserves. However, as the trees began to die and the flow of sugars from the roots into the fungal network diminished, the fungi would switch to a more purely decomposing mode, breaking down dead organic matter in the soil for energy. This transition from symbiont to saprotroph, from partner to decomposer, would happen gradually across the fungal network as individual tree partners died at different rates, the network itself persisting long after the forest canopy had collapsed, continuing to weave through the soil and process organic matter in the dark, a ghost of an ecosystem still performing its biochemical functions in the cold earth below a dying forest. Its filaments threading between the roots of trees that could no longer feed it but had not yet fully gone. Insects, which represent the most species-rich and numerically dominant group of animals on Earth, would respond to the loss of sunlight with a diversity of responses as varied as the group itself. Many insect species have evolved to survive cold winters as eggs, pupae, or dormant adults, entering a state called diapause in which development and metabolic activity are suspended until conditions favorable for activity return. As temperatures plummeted in the weeks following the sun's disappearance, insects in temperate regions would enter diapause en masse, their cold-sensing mechanisms triggering the same response that normally carries them through winter. Tropical insects, which have not evolved the same cold hardiness adaptations because their environment has never required it, would face a more severe immediate crisis, as the temperatures they encounter would fall outside the range they are physiologically capable of tolerating. The diversity of insect life in tropical rainforests, which is the greatest of any terrestrial biome, would be devastated within weeks as temperatures fell to freezing and below, eliminating the extraordinary evolutionary experiment of tens of millions of species that had developed over hundreds of millions of years in the warm, wet equatorial environment that the sun had created and maintained. Marine phytoplankton, the microscopic photosynthetic organisms that form the base of almost all ocean food webs and produce approximately half of the oxygen in Earth's atmosphere, would cease photosynthesizing immediately when sunlight disappeared from the surface ocean, but their physical survival would be governed by the rate at which ocean temperatures fell and by the availability of nutrients. Phytoplankton grow in the sunlit upper layer of the ocean, called the photic zone, which extends to a depth of roughly 200 meters in clear water, and they depend on a combination of light, nutrients, and appropriate temperatures to bloom. Without light, the phytoplankton would stop growing but would not immediately die, continuing to respire and consume their stored organic compounds for a period. As ocean surface temperatures fell, cold-adapted species would persist longer than warm water species, and some phytoplankton have been known to survive in ice as endolithic organisms, living within the brine channels of sea ice and continuing limited photosynthesis, using the tiny amounts of light that penetrate the ice surface. In the permanent darkness of a sunless world, even these ice-adapted survivors would eventually exhaust their options, but their persistence for weeks or months in the freezing ocean would represent one of the last gasps of primary photosynthetic productivity on the planet, the final thread of the food web that had fed the ocean for 3 billion years. Hibernating mammals, including bears, groundhogs, hedgehogs, and many bat species, would enter their dormant state earlier and more deeply than usual as temperatures fell rapidly, and their survival prospects during the weeks of darkness would depend critically on the fat reserves they had accumulated before the event. Hibernation is a state of regulated hypothermia in which core body temperature drops, heart rate slows dramatically, breathing rate decreases, and metabolic rate falls to as little as 5% of normal waking metabolism, allowing an animal to survive for months on stored fat alone. A bear entering hibernation in autumn typically carries enough fat to sustain it through 5 to 6 months of winter, and the gradual deepening of the cold in the weeks after the sun's disappearance would trigger this response in any individual that had accumulated sufficient fat reserves. Animals that had not yet had time to build adequate reserves, particularly those that should have had more weeks of foraging before their natural hibernation season, would face a lethal energy deficit from which their dormancy physiology could not protect them. The timing of the sun's disappearance relative to each species' normal hibernation season would therefore be among the most important factors determining which individuals and populations survived the first winter of the permanent darkness. The behavior of large grazing mammals, including cattle, horses, deer, elephants, and bison, would be profoundly altered by the combination of darkness, dropping temperatures, and the rapid death of the grasses and vegetation they depend upon. Herbivores that graze on living grass and other vegetation would find their food supply beginning to fail within weeks as the green plants died. First the shallow-rooted annuals, and then the deeper-rooted perennials, their stored carbohydrates eventually exhausted. Animals in regions where the ground was freezing would face the additional challenge of foraging through snow and ice for plant material that was increasingly dead and nutritionally depleted. Many large herbivores would begin long instinctive migrations in search of food and warmth, following temperature gradients and scent cues toward the coastlines where ocean heat was keeping temperatures marginally higher for longer. But these migrations would lead into a shrinking and ultimately non-existent habitable zone. The social structures of herd animals would be stressed to the breaking point as food competition intensified, with dominant individuals maintaining access to the last available resources and subordinate individuals being displaced into increasingly inhospitable conditions. The social hierarchies that normally organize these communities becoming instruments of differential survival in the most literal sense. Coral reefs, which are among the most biodiverse ecosystems on Earth, and are built by the calcium carbonate skeletons of coral animals that live in a symbiotic relationship with photosynthetic algae called zooxanthellae, would experience near-immediate crisis when sunlight disappeared. The zooxanthellae that live within coral tissues are responsible for providing up to 90% of the coral's energy through photosynthesis, and without sunlight, they would stop functioning, triggering a bleaching event more severe and immediate than any caused by warming temperatures. The corals would expel their algal symbionts within days, losing their characteristic colors and turning white. And without the energy supply the algae provided, the coral animals would begin to starve. Unlike warming-induced bleaching events, from which corals can sometimes recover if temperatures return to normal within weeks. This bleaching would have no recovery, because the cause was not a stressor that would pass but the permanent absence of the energy source the entire relationship was built around. The reef structures themselves, built from calcium carbonate over thousands of years, would persist for much longer than the living organisms that built them, standing in the cold, dark ocean as skeletal monuments to the most productive marine ecosystems the sunlit world had ever known. The process of seed germination, which is the mechanism by which plant life perpetuates itself across generations, would be affected differently by the loss of sunlight depending on the species and the state of the seed. Seeds in the soil represent a remarkable living archive of plant diversity, with many species producing seeds that can remain dormant for years or even decades, waiting for the right combination of temperature, moisture, and sometimes light to trigger germination. Many seeds do not require light for germination and will sprout in darkness if temperature and moisture conditions are appropriate. But the seedlings that emerge from these seeds would immediately face the problem that they cannot photosynthesize without light, and their initial growth depends entirely on the energy stored in the seed itself, which is sufficient for only a few centimeters of growth. Some seeds are specifically light-dependent germinators, meaning they require a period of illumination to break dormancy, and these would remain dormant even if other conditions were met. The seed banks of the world, both the natural reserves in soil and the deliberate human collections like the Svalbard Global Seed Vault, would represent the most durable legacy of plant life, their contents potentially viable for hundreds of years, waiting in the dark for conditions that, in this scenario, would never arrive. Marine mammals, including whales, dolphins, seals, and walruses, would face an unfolding crisis driven not by the darkness itself, but by the collapse of the marine food web beneath them. Whales that filter feed on krill, small crustaceans that in turn feed on phytoplankton, would find their food supply collapsing within weeks as phytoplankton productivity ceased and krill populations crashed. Great whales, which must consume enormous quantities of krill during summer feeding seasons to accumulate the blubber reserves that sustain them through winter migrations and breeding seasons, would find their summer feeding grounds suddenly devoid of food. Toothed whales and dolphins, which hunt fish and squid using echolocation, would fare better initially because their prey would still be available in the ocean for some time. But as the food web above them collapsed and ocean temperatures fell, fish populations would decline, and the acoustic hunting strategies that cetaceans depend upon would be tested by a changing ocean soundscape. The deep, haunting songs of humpback whales, which travel thousands of kilometers through the ocean and serve complex social and reproductive functions, would continue for a time in the growing cold and dark, the most complex musical communication system in the animal kingdom, sounding across an ocean that was gradually losing the sunlit warmth that had sustained the world those songs were sung to navigate. The human immune system, like all physiological systems, is subject to circadian regulation, with the production of immune cells, the activity of inflammatory responses, and the synthesis of key immune signaling molecules all varying across the 24-hour cycle. The disruption of circadian rhythms caused by the permanent loss of light and dark cycles would affect immune function in ways that are difficult to predict with precision, but that include altered timing of immune responses, changes in the production of melatonin, which has direct immune-modulating effects, and disruption of the cortisol rhythm that normally coordinates the timing of inflammatory responses. Under conditions of extreme cold and stress, immune suppression is a well-documented phenomenon, as the body redirects resources away from immune surveillance and toward more immediate survival priorities like maintaining core temperature. Paradoxically, some aspects of immune function might be enhanced by the cold, as certain immune cells perform better at lower temperatures. The combined effect of circadian disruption, extreme cold, nutritional stress, and psychological trauma on the immune systems of surviving humans would create a complex and unpredictable vulnerability to infectious disease, particularly in the crowded and unsanitary conditions that would develop in the first weeks of the crisis. The behavior of migratory fish species, including salmon and various tuna species, would be disrupted by the collapse of the marine productivity on which their feeding migrations depend, and by the rapid changes in ocean temperature that would alter the thermal gradients they use for navigation. Pacific salmon, which navigate from ocean feeding grounds back to their natal rivers for spawning using a combination of magnetic sensing, olfactory memory, and sensitivity to water chemistry, would find their return journeys increasingly obstructed as rivers began to freeze and water temperatures fell below the range suitable for successful spawning. Many salmon species can survive a range of temperatures, but the combination of freezing rivers, reduced water flow, and the physical barrier of ice would prevent the completion of spawning runs that are essential for the continuation of the population. Atlantic bluefin tuna, which follow temperature gradients and prey distribution across thousands of kilometers of ocean, would find their preferred thermal niches compressed and ultimately eliminated as ocean temperatures fell uniformly, forcing populations into increasingly marginal conditions near the equator where residual warmth persisted longest, crowding multiple species into a shrinking warm band before that band too finally closed. The psychological impact on human populations of the permanent loss of sunlight would constitute an unprecedented mass mental health crisis, for which no existing framework of emergency response would be adequate. Seasonal affective disorder, a well-documented pattern of depression that occurs in response to reduced winter sunlight at high latitudes, is mediated by disrupted serotonin and melatonin signaling in the brain, both of which are regulated by light exposure. The permanent elimination of all sunlight would produce a version of this disorder in essentially the entire human population simultaneously, compounded by the trauma of the event itself, the loss of the normal structures of daily life, the collapse of food systems and infrastructure, and the existential terror of understanding that the situation was permanent. Research on human psychological responses to extended polar night, to submarine missions, and to simulated isolation experiments suggests that circadian disruption alone produces significant cognitive impairment, mood disturbance, and social dysfunction within days. And the combination of these effects with the broader catastrophe would challenge the psychological resilience of individuals and communities in ways that would be among the most important determinants of survival outcomes in the weeks and months following the event. Amphibians, which include frogs, toads, salamanders, and caecilians, would be among the most immediately vulnerable vertebrate groups following the sun's disappearance, because their ectothermic physiology makes them entirely dependent on environmental heat for their metabolic functioning. Unlike mammals and birds, which generate their own body heat through endothermy, amphibians rely on external sources of warmth to maintain the temperatures at which their metabolic enzymes function efficiently. And as ambient temperatures fell toward freezing in the weeks following the sun's disappearance, their body temperatures would fall in parallel, slowing their metabolism, impairing their immune function, and eventually pushing them into a cold-induced torpor from which many would not emerge. Species that already experience seasonal cold at high latitudes have evolved varying degrees of freeze tolerance or freeze avoidance, with some frogs capable of surviving the freezing of up to 65% of their body water by producing cryoprotectant compounds like glucose that prevent ice crystal formation in their cells. These cold-adapted species would survive longest, their antifreeze chemistry buying them time in temperatures that would kill their tropical relatives within days. The biochemical ingenuity of evolution, providing a temporary stay of execution in a world growing uniformly cold. The soil ecosystems of the world's agricultural lands, which have been intensively managed for millennia to support the growth of food crops, would face a cascade of failures in the weeks following the sun's disappearance that would be distinct from those of natural ecosystems. Agricultural soils typically have lower organic matter content than natural soils due to repeated cultivation and harvesting, meaning they carry less stored energy for the soil organism community. The crops growing in those soils at the time of the event would die within days to weeks as photosynthesis ceased and temperatures fell, leaving behind root systems and stem material that would provide some temporary substrate for decomposers. Stored grain reserves, which represent the primary buffer between crop failure and human starvation, and which at any given time amount to approximately 2 to 3 months of global food supply, would become the most important material resource for human civilization, and the speed with which governance structures could organize equitable distribution of those reserves would be among the most critical determinants of how many people survived the first months of the darkness. The chemosynthetic ecosystems of deep-sea hydrothermal vents, which derive their energy not from sunlight, but from the chemical energy of reduced compounds like hydrogen sulfide emitted from the seafloor, would be essentially unaffected by the loss of solar radiation. These remarkable communities, discovered only in 1977, and representing a completely independent origin of ecosystem productivity, support dense populations of specialized organisms including tube worms up to 2 meters long, giant clams, shrimp with light-sensing organs on their backs, and a diverse microbial community that forms the base of the food web. Because the energy driving these ecosystems comes from Earth's internal heat rather than from the sun, they would continue to function with little direct disruption, becoming the only fully functional ecosystems on the planet within weeks of the sun's disappearance. They would not, however, be able to support or rescue any of the surface life that depended on sunlight, because they exist at depths of 2,000 to 4,000 meters in conditions of extreme pressure and temperature that are lethal to all surface organisms. They would carry on in their alien magnificence, entirely self-sufficient, entirely isolated, the last independently functioning ecosystems on a dying planet, burning hydrogen sulfide in the permanent dark, as they had done for millions of years before the first photosynthetic organism ever made oxygen. The response of bird species to the permanent loss of sunlight would vary enormously based on their ecology, physiology, and geographic location, but virtually all would face severe challenges within weeks. Diurnal birds, which are active during daylight hours and use visual cues for foraging, communication, predator detection, and navigation, would be most immediately affected, as their entire behavioral repertoire is organized around the presence of light. Some species might adapt their foraging behavior toward the dawn and dusk periods, when starlight provided minimal illumination, but the prey they depend upon would also be declining rapidly as the food web collapsed below them. Birds that eat seeds and grains would find their food supply more persistent than birds that eat insects or fruit, because seeds can survive for months or years and represent a more durable food resource than living prey. However, the rapidly falling temperatures would impose physiological demands on small birds, which have a high surface area to volume ratio and lose heat rapidly. That would require them to maintain high food intake even as food availability declined, a cruel arithmetic that would eliminate many small species within weeks, their rapid metabolisms and small fat reserves leaving them no margin for the double pressure of cold and hunger, simultaneously closing in. The human microbiome, the vast community of bacteria, archaea, fungi, and viruses that inhabit the human body and contribute to digestion, immune function, and many other physiological processes, would be indirectly affected by the loss of sunlight through changes in diet, temperature, stress hormones, and circadian disruption. The gut microbiome in particular is known to have its own circadian rhythm, with different species becoming more or less abundant at different times of day in response to the timing of meals, the presence of light-regulated host hormones, and the activity patterns of the gut itself. Research has shown that circadian disruption in the host produces measurable changes in the composition and function of the gut microbiome, which in turn affects metabolic health, immune function, and mood. Under conditions of severe dietary restriction and stress, the human microbiome changes rapidly, with species adapted to low-fiber, high-fat survival diets becoming more prevalent, and species that thrive on a diverse plant-rich diet declining. These changes would affect the health of survivors in complex ways, altering their ability to extract nutrition from whatever food remained available, their immune responses to infection, and even their neurological and emotional states through the gut-brain axis that connects the microbiome to the central nervous system. The phenomenon of bioluminescence, the production of visible light by living organisms through chemical reactions involving compounds called luciferins and enzymes called luciferases, would take on a new significance in a world without sunlight. Bioluminescence is widespread in the deep ocean, where it is estimated that 76% of marine species are capable of producing their own light, using it for communication, predator avoidance, camouflage, and luring prey. In the permanent darkness of a sunless ocean, the deep-sea bioluminescent community would continue to function as it always had, its members flickering and flashing in the cold, dark water in the same behavioral patterns they had evolved over hundreds of millions of years. In shallower waters and at the surface, the bioluminescent dinoflagellates that create the magical blue glow, sometimes seen in disturbed ocean water at night, would continue to flash as long as the water was warm enough for them to survive, creating brief moments of cold blue light in an otherwise totally dark ocean, organic light in a world where the original source of all light had vanished. the living ocean making its own small illumination in the absence of the star that had always outshone it before. Let the biological world settle now into the quiet of its darkness. The trees are drawing inward, the insects are stilling, the whales are moving through a cooling ocean toward warmth that is retreating from them. These lives are not ending dramatically but slowly. The way a fire reduces not to a sudden cold but to a long dimming of embers, each species finding its own pace, its own depth of reserves, its own ancient strategy for the dark. You do not need to grieve what is happening in the script tonight. You are simply the observer, warm and still, listening from a safe and comfortable distance to a story that is also somehow the story of life itself, its resilience, its ingenuity, its patience. Let the cold that is spreading across the imagined world in this story be only a concept to you, not a feeling. Let the warmth of where you are now fill the space between each thought. The biological world is resting, in its way, and you are resting in yours, and the next part of our journey will take us deeper still, into the stone and salt and chemistry of the planet itself, where the changes are slower and more ancient and more vast. The permafrost that underlies approximately 25% of the northern hemisphere's land surface, a layer of soil and rock that has remained continuously frozen for thousands of years, and that stores an estimated 1.5 trillion tons of organic carbon, would paradoxically be preserved and extended by the loss of the sun rather than threatened. Under current conditions, rising global temperatures are thawing permafrost at an accelerating rate, releasing methane and carbon dioxide as ancient organic matter decomposes, contributing to further warming in a dangerous feedback loop. In a sunless world, the reverse would happen with astonishing speed. The active layer of soil above the permafrost, which normally thaws each summer to allow plant growth and nutrient cycling, would freeze permanently within the first months, adding to the depth of the permafrost layer rather than reducing it. The vast organic carbon stores locked in permafrost, including the remains of woolly mammoths, ancient forests, and millennia of accumulated plant material, would be sealed ever deeper in frozen ground, removed from the carbon cycle not gradually, but suddenly and completely. A vast archive of ancient life pressed deeper into cold storage by a world that was becoming one enormous permafrost layer from the surface down. The chemical weathering of rocks, one of the most important geological processes regulating the long-term carbon cycle and the composition of Earth's atmosphere over millions of years, is driven primarily by the interaction of rainwater, carbon dioxide, and silicate minerals, a set of reactions that proceed much faster at higher temperatures. As global temperatures plummeted in the months following the sun's disappearance, chemical weathering rates would drop dramatically, slowing the consumption of atmospheric carbon dioxide by silicate rock reactions. This matters because over geological timescales, silicate weathering is the primary mechanism by which carbon dioxide is removed from the atmosphere and sequestered in the form of carbonate minerals. And it is the slow balance between this weathering sink and volcanic outgassing of carbon dioxide that has maintained Earth's atmospheric composition within the narrow range suitable for life over billions of years. The near cessation of chemical weathering would remove one of the planet's most ancient climate-regulating mechanisms. But given the much faster collapse of all other life-supporting systems, the timescale of geological weathering would be largely irrelevant to the immediate crisis of survival playing out on the frozen surface above. Volcanic activity, which is driven by the internal heat of the Earth rather than by solar energy, would continue entirely unaffected by the loss of the sun, and the gases emitted by volcanoes would play an increasingly important role in the chemical evolution of the atmosphere in the months and years following the event. Volcanoes emit a mixture of gases including water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other compounds. And these emissions represent the primary geological source of both greenhouse gases and atmospheric sulfur. In a world where photosynthesis had ceased and the biological cycling of carbon had stopped, volcanic emissions would become a more prominent component of the remaining atmospheric chemistry, slowly adding carbon dioxide and water vapor to an atmosphere that was otherwise becoming progressively more depleted of these compounds as they were absorbed by the cooling ocean and frozen out at the poles. The sulfur dioxide from volcanic eruptions, which normally reacts with water vapor in the atmosphere to form sulfate aerosols that reflect sunlight back to space, would have no sunlight to reflect, but would still affect atmospheric chemistry by combining with water to form sulfuric acid droplets that would contribute to acid precipitation over the cold landscape beneath active volcanic regions. The ocean's carbonate chemistry, which regulates the pH of seawater, and the ability of marine organisms to build shells and skeletons from calcium carbonate, would undergo significant changes in the months following the sun's disappearance. As ocean temperatures fell, the solubility of carbon dioxide in seawater would increase, causing the ocean to absorb more atmospheric carbon dioxide and driving the formation of carbonic acid, which would decrease the pH of the seawater and increase its corrosiveness toward calcium carbonate minerals. This ocean acidification process, which is already occurring due to anthropogenic carbon dioxide emissions, would proceed differently in a cooling, sunless ocean because the dynamics of biological carbon cycling would be completely altered. With phytoplankton productivity collapsed and the biological pump that normally exports organic carbon to the deep ocean shut down, the distribution of carbon between the surface and deep ocean would change, altering the carbonate saturation state throughout the water column. The shells and skeletons of the marine organisms that had been building calcium carbonate structures for hundreds of millions of years would begin to dissolve in the increasingly acidic water, the ocean slowly consuming the mineral record of its own biological history. The behavior of Earth's tectonic plates would not be directly altered by the loss of the sun, because plate tectonics is driven entirely by the internal heat of the planet, specifically by the slow convection of the mantle, the radioactive decay of elements like uranium, thorium, and potassium in the deep interior, and the residual heat left over from Earth's formation 4.5 billion years ago. The rate of seafloor spreading at mid-ocean ridges, the subduction of oceanic plates beneath continental margins, and the slow collision and separation of continents would continue on their geological timescales completely undisturbed by events at the surface. However, the surface expressions of tectonic activity, including earthquakes and volcanic eruptions, would interact with the freezing surface in new ways. The isostatic adjustment of the crust in response to the growing weight of ice sheets, a process called glacial isostatic adjustment that occurs as the lithosphere flexes under the changing distribution of surface mass, would begin to affect the stress state of the crust, with areas of growing ice loading becoming compressed and areas of ice removal experiencing rebound, potentially triggering earthquakes along pre-existing fault systems in regions where the ice load was changing most rapidly. The nitrogen cycle, which circulates the element nitrogen through the atmosphere, soil, water, and living organisms, and is essential for the production of proteins and nucleic acids in all living things, would be profoundly disrupted by the collapse of biological activity in the months following the sun's disappearance. Nitrogen fixation, the conversion of atmospheric nitrogen gas into forms that organisms can use, is performed primarily by specialized bacteria in the soil and in the root nodules of leguminous plants, and these bacteria would progressively cease their activity as soil temperatures fell below the range in which their enzymes function efficiently. The denitrification process, by which other bacteria convert fixed nitrogen compounds back into atmospheric nitrogen gas, would also slow dramatically with falling temperatures. The net effect would be a gradual accumulation of fixed nitrogen compounds in frozen soils and in the increasingly cold ocean, locked into forms that would be inaccessible to any remaining organisms. Another essential element of the biochemistry of life becoming frozen into geological storage. The planet's chemistry consolidating itself into a cold, stable, biologically inert state that in certain ways resembled the chemistry of the early Earth before life had developed the metabolic pathways to transform it. The behavior of methane, a potent greenhouse gas that is produced by methanogenic archaea in anaerobic environments like wetlands, the guts of ruminant animals, and the seafloor, would change in complex ways in the months following the sun's disappearance. In the short term, the freezing of wetlands across the northern hemisphere would trap methane that would otherwise have been released into the atmosphere, as the frozen surface layer acted as a seal over the anaerobic microbial communities below. However, in the deep ocean, enormous quantities of methane are stored in a solid form called methane clathrate or methane hydrate, a crystalline structure in which methane molecules are trapped within cages of water ice that is stable only at high pressure and low temperature. As ocean temperatures fell in the months following the sun's disappearance, the stability of these methane clathrate deposits on the seafloor would actually be enhanced rather than threatened, the colder water temperatures pushing them deeper into the stability zone and potentially capturing additional methane that had been on the margin of stability. The vast methane stores of the deep ocean would be locked more securely into their icy cages by the cooling, a geological freezer tightening its grip on a greenhouse gas that would otherwise transform the atmosphere if released. The chemistry of the upper atmosphere, specifically the stratosphere and mesosphere, would continue to evolve in the months after the sun's disappearance as photochemical reactions ceased, and the remaining reactive molecules underwent transformations driven by the background flux of cosmic radiation and the emissions of radioactive elements. The ozone layer, as previously noted, would be depleted by reactions with nitrogen oxides and chlorine compounds without the ultraviolet radiation needed to regenerate it, and the stratosphere would gradually become a more chemically simple place, dominated by the stable, unreactive gases like nitrogen and argon that make up the bulk of the atmosphere, and that are largely unaffected by the absence of sunlight. The mesosphere, the layer from roughly 50 to 85 kilometers altitude, where temperatures reach their lowest point in the atmosphere due to the absence of ozone heating, would see its temperature structure change as the ozone layer below it disappeared, removing the heat source that had maintained the mesosphere's characteristic temperature profile, and allowing the entire upper atmosphere to cool toward a more uniform cold that extended from the surface to the edge of space. The weathering of exposed rock surfaces by physical processes, including freeze-thaw cycling, thermal expansion and contraction, and the mechanical action of ice, would intensify dramatically in the months following the sun's disappearance as temperatures oscillated around the freezing point during the transitional period, before settling into a permanent deep freeze. Freeze-thaw weathering occurs when water seeps into cracks in rock, freezes and expands by approximately 9% in volume, exerting pressures of up to 2,000 atmospheres on the surrounding rock, and then thaws and contracts, gradually widening the crack with each cycle. In a world where temperatures were falling through the freezing point repeatedly, as the climate transitioned toward permanent deep cold, rock surfaces that had been relatively stable under consistent temperatures would experience intense mechanical stress, producing abundant rock fragments and angular debris. Mountain peaks and cliff faces would become more unstable, with increased rockfall and talus production in the early months, the physical disintegration of exposed rock surfaces accelerating before eventually being stilled and preserved under the advancing ice sheets. The landscape locked into whatever form it had reached at the moment the ice finally covered it completely. The behavior of groundwater systems, the vast reservoirs of water stored in aquifers beneath the surface, would be affected in the months following the sun's disappearance by the freezing of surface recharge zones and by the pressure changes associated with the increasing weight of overlying ice. Most shallow aquifers are recharged by the infiltration of rainwater and snowmelt through the soil, a process that would progressively shut down as the surface froze and precipitation fell as snow that accumulated rather than infiltrated. The upper portions of aquifers in regions of rapid cooling would begin to freeze from above, with the freezing front advancing downward through the saturated zone, potentially trapping pockets of unfrozen groundwater under pressure that could cause artesian conditions or ground heave. Deeper aquifers, particularly those in bedrock at significant depth, would be insulated from the surface cooling by the thermal mass of the overlying rock and would remain liquid for much longer, potentially for years or even decades, representing a hidden reserve of liquid water far beneath the frozen surface, a geological feature whose existence would become critically important to any organisms or human communities that somehow survived long enough to find and access it. The process of soil formation, called pedogenesis, which creates the thin layer of fertile soil that supports nearly all terrestrial food production through the slow weathering of parent rock material and the accumulation of organic matter from decaying organisms, would effectively cease in the months following the sun's disappearance. Soil formation depends on the combined activity of physical weathering, chemical weathering, and biological activity, particularly the decomposition of organic matter by bacteria and fungi, and the physical mixing of mineral and organic material by earthworms and other soil organisms. As temperatures fell below freezing and biological activity ceased, the processes of soil formation would stop, and the existing soils of the world would be preserved under ice in essentially the state they were in at the moment of the sun's disappearance. some of the world's most fertile agricultural soils, including the Chernozems of Ukraine and Russia, the mollisols of the American Great Plains, and the volcanic soils of Indonesia, represent thousands of years of pedogenic processes and biological enrichment, and their preservation under ice would mean that they remained available, potentially, for any future scenario in which the surface eventually warmed again, though the geological and astronomical likelihood of that scenario is vanishingly small. The carbon stored in the world's forests and other terrestrial vegetation, estimated at approximately 550 billion tons of carbon in living biomass, would begin a complex journey through the environment in the months following the sun's disappearance as vegetation died, and the organisms that decompose it responded to the changing conditions. In tropical regions, where decomposition rates are normally very high due to warmth and moisture, the sudden cooling would slow decomposition dramatically before it could break down much of the dead biomass, leaving an enormous quantity of intact dead organic matter standing and lying across former forest landscapes. In temperate regions, the timing of the sun's disappearance relative to the normal seasonal cycle would determine how much decomposition occurred before temperatures fell too low for it to continue. The organic carbon that was not decomposed would ultimately be buried under ice and snow, removed from the short-term carbon cycle, and stored in a form that could persist for millions of years, joining the geological record of previous ice ages as organic-rich layers in the sedimentary record, a compressed diary of the biosphere's final chapter written in molecules of carbon that had once been leaves and trunks and roots reaching toward a sun that was no longer there. The world's salt flats and evaporite deposits, geological formations created by the evaporation of ancient inland seas and lakes, would no longer be forming new material without the solar energy that drives evaporation, but the existing deposits would be buried under snow and ice and preserved in essentially their current state. More interesting from a geochemical perspective would be the behavior of saline lakes and inland seas like the Great Salt Lake, the Dead Sea, and the Caspian Sea in the months following the sun's disappearance. These water bodies, which are already hypersaline because evaporation has concentrated their dissolved salts over time, would experience a dramatic reduction in evaporation as temperatures fell. But their surfaces would not freeze as readily as freshwater lakes, because the high salt content depresses the freezing point of water, with the Dead Sea's extreme salinity of approximately 340 grams of salt per liter, keeping it liquid to temperatures far below 0 degrees Celsius. These hypersaline basins would therefore persist as liquid water bodies longer than any freshwater system, cold and dark, and increasingly concentrated, as what little evaporation continued removed water without salt, their ancient brine becoming a chemical record of the dying world above them, preserving a last liquid chemistry in basins carved by geology and maintained by sun that was now gone. The behavior of Earth's magnetic field over the months following the sun's disappearance would be largely unaffected by the loss of solar energy, because the geomagnetic field is generated by the convection of molten iron and nickel in Earth's liquid outer core, a process driven by internal heat that is entirely independent of solar radiation. The main variations in the magnetic field that occur over months and years, including the slow drift of the magnetic poles and the secular variation in field intensity, would continue on their geological timescales undisturbed. What would change is the external component of the magnetic field, the part influenced by the solar wind and by currents in the ionosphere that are driven by solar radiation. As the solar wind faded and the ionosphere collapsed, these external contributions to the measured magnetic field would disappear, leaving only the core-generated internal field. For any surviving organisms or instruments sensitive enough to detect the magnetic field, the quality of the magnetic signal would actually improve in some respects, becoming cleaner and more stable as the noisy external contributions faded away. A quieter and more reliable guide for any magnetic navigator who somehow still had reason to navigate across the frozen dark world that the planet had become. The chemistry of rain and snow falling in the months following the sun's disappearance would change as atmospheric chemistry evolved and industrial and biological sources of pollutants and nutrients ceased. Normal rainwater is slightly acidic due to its equilibrium with atmospheric carbon dioxide, forming weak carbonic acid, and in industrialized regions, it carries additional acidity from sulfur and nitrogen oxides emitted by human activity. As industrial activity ceased in the crisis, these anthropogenic inputs would fade, and precipitation chemistry would become simpler and closer to the theoretical baseline of pure water in equilibrium with whatever gases remained in the atmosphere. Volcanic emissions would continue to contribute sulfur dioxide and hydrogen sulfide, and the reactions of these gases with atmospheric water vapor would produce sulfuric and sulfurous acid, making precipitation near volcanic regions moderately acidic even without industrial input. The snowpack accumulating on the frozen surface would preserve this chemical record in its layers, just as ice cores from Greenland and Antarctica preserve the chemical history of the atmosphere over hundreds of thousands of years, the falling snow writing its record into the growing ice sheet, layer by layer, an unread diary of a dying world's final atmospheric chemistry accumulating in silence and cold. The geothermal heat flux emerging from the Earth's interior, which averages approximately 87 milliwatts per square meter across the continental surface, and somewhat higher at mid-ocean ridges and volcanic regions, would become the dominant heat source for the planet's surface environment as solar radiation ceased. Under normal conditions, geothermal heat contributes less than 0.1% of the total heat budget at the surface, completely overwhelmed by solar input. But in a sunless world, its contribution would be the only continuous heat input to the surface system. The practical implications of this residual heat would be modest in terms of surface temperatures, since 87 milliwatts per square meter is approximately 6,000 times less than the average solar input, and would support a mean surface temperature of roughly negative 240 degrees Celsius in the absence of any atmosphere, far colder than the actual temperatures that would be maintained by the residual heat in the atmosphere and ocean. However, in specific geological settings where geothermal heat is concentrated, such as the volcanic regions of Iceland, Yellowstone, New Zealand, and the East African Rift, the heat flux would be enough to maintain patches of ice-free liquid water, small thermal oases in the frozen landscape, warm springs and mud pools and fumaroles steaming in the cold, dark air, potential refugia for any thermophilic organisms that could reach them, and any others for whom a few degrees above freezing was enough. The long-term chemical evolution of Earth's atmosphere in the months following the sun's disappearance would be shaped by the gradual drawdown of oxygen produced by billions of years of photosynthesis and the cessation of new oxygen production. The current atmospheric oxygen concentration of approximately 21% by volume represents the accumulated product of photosynthetic organisms over roughly 2.4 billion years. Since the Great Oxidation Event, when photosynthetic bacteria first began to significantly increase atmospheric oxygen levels. With photosynthesis ceased, the sources of new oxygen would be gone, while the chemical reactions that consume oxygen, including the respiration of any surviving organisms, the oxidation of reduced chemical species in volcanic gases, and the slow chemical weathering of iron-bearing minerals, would continue. The rate of oxygen consumption by these abiotic processes is very slow relative to the total atmospheric oxygen reservoir, meaning that the oxygen concentration would take millions of years to fall to levels threatening to any remaining biology, making atmospheric oxygen depletion largely irrelevant to the immediate and medium-term fate of life on a planet already dying from cold and darkness, rather than from lack of oxygen. The air of the frozen world would remain breathable, if breathable could be considered relevant to a world in which nothing needed to breathe into it. The process of fossilization, by which dead organisms are preserved in the geological record, would be dramatically altered in the months and years following the sun's disappearance. Normal fossilization requires rapid burial of an organism in sediment before scavengers and decomposers can destroy the remains, and the preservation quality depends on the chemistry of the burial environment. In a world rapidly freezing over, the cryogenic preservation of organisms under expanding ice sheets would represent a new and extraordinarily effective form of fossilization, far more complete than the mineralization processes that normally preserve hard parts and occasional soft tissues. The organisms caught in the expanding ice would be preserved with a completeness that would make even the most exquisitely preserved amber inclusion look crude by comparison. Their cells intact, their proteins preserved, their last meals frozen in their stomachs, their final postures captured in ice that might hold them for millions of years if the planet's deep freeze were eventually interrupted by some source of warming from beyond the solar system. The frozen world would become a museum of itself, every species a specimen, every landscape a diorama, the entire biosphere of the last sunlit world preserved in cold storage for whatever audience the universe might eventually send to read it. Now let the geology settle into stillness around you. The rocks are freezing, the aquifers are sealing, the volcanic warmth is rising through the cold in small and stubborn spirals. These are the slowest transformations, measured not in moments but in months and centuries, and your mind can hold them lightly, the way you might hold the memory of a landscape you once passed through without stopping. The chemistry of the atmosphere is simplifying itself, the way a complex thought simplifies into a feeling as you move deeper towards sleep, and the feeling that remains is something like vastness, something like patience. The planet is not panicking. It is changing, the way everything changes, slowly and without announcement, layer by layer, degree by degree. Let that slowness move through you now. Let the geological time of this story press gently on your thoughts until the thoughts themselves become as slow and deep as stone. The final part of our journey is just ahead, out into the years and the centuries and the deep dark silence of a solar system without its sun, and you will hear it from somewhere very restful, somewhere very still. In the years following the sun's disappearance, Earth would continue moving through the galaxy in a straight line at approximately 29.78 kilometers per second. The velocity it had at the moment the gravitational constraint of the sun was removed, carrying it away from the center of what had been the solar system and outward into the interstellar medium at a speed that sounds impressive, but that covers only about 940 million kilometers per year, a distance equivalent to roughly 6 times the former distance between the Earth and the Sun. On the timescale of interstellar travel, this is extraordinarily slow. The nearest star to our former solar system, Proxima Centauri, is approximately 4.24 light-years away, which translates to roughly 40 trillion kilometers. And at Earth's current velocity, it would take the planet approximately 43,000 years to reach that distance, even if it were traveling directly toward it, which it almost certainly would not be. Earth would instead wander through the galaxy on a trajectory determined entirely by its velocity at the moment of release, a dark frozen world drifting through interstellar space with no destination and no star to orbit, carrying its frozen oceans and its silent continents and its perfectly preserved ecosystem of ice into the cold between the stars. The Moon, which orbits Earth rather than the Sun directly, would remain gravitationally bound to Earth after the Sun's disappearance, continuing to orbit its parent planet as the pair drifted together through interstellar space. The Moon's orbit around Earth is maintained by the gravitational attraction between their masses, which is entirely independent of the Sun, and this relationship would persist unchanged as both bodies journeyed together away from their former stellar home. The tidal interaction between Earth and the Moon, which has been very slowly transferring angular momentum from Earth's rotation to the Moon's orbit, and causing the Moon to recede from Earth at approximately 3.8 centimeters per year, while Earth's rotation very gradually slows, would continue on its ancient timescale, the Moon moving fractionally further from Earth with each passing year regardless of the absence of the Sun. In the cold darkness of interstellar space, the Earth-Moon system would represent a tiny gravitational partnership, two frozen worlds circling each other in the dark, the smaller one dark and airless, the larger one wrapped in a frozen atmosphere and covered in ice kilometers thick, both of them carrying the genetic material of billions of species preserved in cold storage, a biological archive drifting through the void. The other planets of the former solar system would each be released from their orbits at the moment the Sun's gravitational influence ceased to reach them, each at a time determined by their distance from the Sun divided by the speed of light. Mercury, the innermost planet, would feel the gravitational release approximately 3.2 minutes after the Sun disappeared. Venus would be released at approximately 6 minutes. Mars, farther out than Earth, would continue its orbit for approximately 12.5 minutes before the news arrived, and it too straightened into a linear trajectory. Jupiter, the largest planet, would orbit for approximately 43 minutes before its release. Saturn would orbit for approximately 79 minutes, Uranus for approximately 2 hours and 40 minutes, and Neptune for approximately 4 hours and 10 minutes. Each planet would then travel in whatever direction its orbital velocity happened to be pointing at the moment of release, and within years, the orderly arrangement of the solar system would dissolve into a scattering of independent dark worlds moving in different directions through the galaxy. The architectural masterpiece of gravitational physics that had organized them for 4.5 billion years coming apart in the geologically instantaneous interval of a few hours. like a mobile hanging from a ceiling whose thread had been cut. The asteroid belt between Mars and Jupiter, which contains millions of rocky bodies ranging from dust particles to the dwarf planet Ceres, would also be released from solar gravity over the course of approximately 30 to 60 minutes, depending on the distances of individual bodies, and its constituents would scatter into independent trajectories through the galaxy. The gravitational influence of Jupiter, which is the most massive planet in the solar system, and whose gravity has long been understood to play a role in shaping the asteroid belt and deflecting some potentially hazardous objects away from the inner solar system, would itself diminish as Jupiter moved away from the former asteroid belt region, and the mutual gravitational interactions of the remaining asteroids would gradually change the distribution of those objects over thousands of years. Some asteroids might follow trajectories that eventually brought them close to Earth's path through interstellar space, though the probability of a collision at the scale of the galaxy is extremely small. The vast distances between objects in space ensuring that even in the apparent chaos of a dissolved solar system, the chance of any two specific objects meeting remains vanishingly unlikely. The temperature of Earth's surface in the years following the Sun's disappearance would eventually stabilize at the level supported by geothermal heat alone, which, as previously noted, would be extraordinarily cold. But the transition to that final temperature would take decades rather than years because of the enormous thermal mass stored in the ocean. The ocean, with an average depth of approximately 3.7 kilometers and a volume of roughly 1.335 billion cubic kilometers of water, holds an almost incomprehensible quantity of thermal energy. And even as its surface froze and its upper layers cooled rapidly, the deep ocean would release its heat gradually over years and decades, delaying the arrival of the final equilibrium temperature. Climate models that have explored this scenario suggest that the surface temperature over the frozen oceans would approach approximately -20 degrees Celsius within about 10 years, and the final deep ocean temperature would approach its current value of 2 to 4 degrees Celsius at the bottom, preserved by the insulating ice above and the minimal geothermal flux from below for potentially thousands of years. The planet would not reach its final cold equilibrium quickly, the ocean acting as a slow thermal battery, discharging its accumulated solar energy into the dark over a geological moment that would still span human generations. Any liquid water remaining on or near the surface of the planet in the years following the Sun's disappearance would be found exclusively in geothermally heated environments, including the hydrothermal springs and volcanic lakes mentioned earlier, and the geothermally warmed regions beneath the Antarctic and Greenland ice sheets. It is already known that liquid water exists beneath the Antarctic ice sheet in the form of subglacial lakes, the largest of which, Lake Vostok, lies beneath approximately 4 kilometers of ice and has been isolated from the surface for an estimated 15 to 25 million years, yet maintains liquid water due to the combination of geothermal heat and the insulating weight of the ice above it. In a frozen, sunless world, these subglacial lakes would expand as the overlying ice thickened and increased the pressure on the ice-water interface, potentially creating a network of liquid water environments beneath the growing continental ice sheets that could persist for millions of years. The microbial communities already documented in existing subglacial lakes, which include chemolithotrophic bacteria that derive energy from chemical reactions involving minerals rather than from organic matter or sunlight, would represent the most persistent potential refugia for life on the frozen Earth, carrying on in their cold, dark liquid world with the same unhurried biochemistry they had been practicing since long before humans appeared on the surface above them. The question of whether any multicellular life could survive the permanent freezing of the Earth's surface over years and decades leads to a consideration of the most extreme survivors known in biology, the tardigrades, microscopic animals, sometimes called water bears, that are renowned for their ability to survive conditions that would instantly kill any other animal. Tardigrades can survive complete desiccation by entering a cryptobiotic state called anhydrobiosis, in which they lose almost all their body water, and their metabolism drops to less than 0.01% of normal, and they can remain in this state indefinitely until rehydrated. They can survive temperatures from near absolute zero to above 150 degrees Celsius, pressures 6 times greater than the deepest ocean trench, and radiation levels hundreds of times the lethal dose for humans. In a freezing world, tardigrades in their cryptobiotic state embedded in ice or frozen soil would survive essentially indefinitely, their cellular machinery in a perfect state of suspended animation, waiting with the same patient biochemical indifference that characterizes all truly extremophilic life for conditions that would allow them to rehydrate and resume their microscopic lives. They would not be conscious of waiting, they would not suffer or hope, they would simply persist, the most indestructible passengers on a frozen ship sailing through the dark, carrying in their microscopic bodies the proof that life, once it begins, is extraordinarily reluctant to entirely end. The trajectory of Earth through the galaxy over thousands and millions of years after the Sun's disappearance would be governed by the gravitational field of the Milky Way itself, and Earth would continue to orbit the galactic center much as it always has, since its galactic orbital velocity is approximately 220 kilometers per second and is only marginally affected by the loss of the Sun's gravitational contribution to the local dynamics. The galaxy's gravitational potential well, maintained by hundreds of billions of stars and vast quantities of dark matter, would keep Earth in a roughly circular orbit around the galactic center, with a period of approximately 225 to 250 million years, the same galactic year that has timed the great cycles of Earth's geological and biological history. Over millions of years, Earth's straight-line trajectory through interstellar space would be gradually curved by the collective gravity of nearby stars and molecular clouds, eventually settling into a new galactic orbit shaped by whatever gravitational influences it encountered. A world without a star becoming just another dark body in the galactic disk, classified by any sufficiently advanced astronomical civilization as a rogue planet. One of the hundreds of billions of such worlds that are estimated to drift through the Milky Way unattached to any stellar system. The probability of Earth encountering another star or planetary system during its journey through interstellar space is extraordinarily low on any human timescale. But over millions and billions of years, the possibility becomes more significant. The average distance between stars in the neighborhood of the former solar system is approximately 4 to 8 light years, and the density of stars increases somewhat toward the galactic center. But even in the most stellar-rich regions, Earth would typically travel for millions of years between close stellar encounters. A close encounter in this context means an approach within a few light years, which would be gravitationally significant enough to perturb Earth's trajectory, but unlikely to result in capture into a new stellar system without very specific conditions of relative velocity and approach angle being met. If Earth were to pass within the habitable zone of a new star, defined as the range of distances at which liquid water could exist on the surface given the star's luminosity, the frozen planet's ice would begin to melt, the atmosphere would warm, and conditions might theoretically allow for the reactivation of life from the preserved genetic material in its frozen depths. A scenario so improbable that it borders on mythology, but that physics does not technically forbid. The concept of a rogue planet potentially supporting life in the absence of stellar energy has been seriously explored by planetary scientists, and the conclusions are surprising in their relative optimism about certain scenarios. A planet with an initial mass similar to Earth, but with a much thicker hydrogen and helium atmosphere, captured from a solar system during formation, could potentially maintain surface temperatures above freezing through the greenhouse effect of that thick atmosphere for billions of years, without any stellar heat source. Earth itself does not have such a thick primordial atmosphere, having lost most of its hydrogen and helium early in its history, and the greenhouse effect of its current atmosphere of nitrogen, oxygen, carbon dioxide, and water vapor would not be sufficient to maintain liquid water without solar input. However, the interior of a rogue Earth, maintained by radiogenic and residual heat, combined with the insulating effect of kilometers of ice acting as a thermal blanket over deep liquid water, could in principle maintain liquid water environments similar to those that might exist on icy moons like Europa and Enceladus, which harbor subsurface oceans maintained by tidal heating in the absence of direct sunlight. Life in those hypothetical deep liquid zones would be chemically plausible, if extraordinarily reduced in complexity compared to the sunlit surface biosphere that had preceded it. The fate of the information encoded in the DNA of the species that had lived on Earth before the sun's disappearance represents one of the most poignant aspects of the cosmic scenario we are exploring. Molecule under cold, dry, dark conditions, and ancient DNA has been recovered from permafrost-preserved mammoths, horses, and even early modern humans that died tens of thousands of years ago, with fragmented but sequenceable genetic material surviving in bones and tissues preserved in Arctic sediments. In a permanently frozen Earth, the genetic material of every species that had lived at the time of the sun's disappearance would be preserved in the ice, in the frozen soil, in the crystalline tissues of cryogenically preserved organisms, potentially for millions of years. The complete evolutionary record of 4 billion years of life on Earth encoded in molecules of adenine, thymine, guanine, and cytosine embedded in ice a kilometer thick. The library of life would be intact, unread, waiting, written in the most fundamental chemical language the universe has ever produced, stored in a medium more durable than any human archive, on a world that had become its own tomb and its own memorial simultaneously. The eventual fate of the sun itself, if it had simply disappeared through some mechanism we have not specified rather than through its natural stellar evolution, would leave behind whatever remnant its mass had become. But for the purposes of this thought experiment, let us consider the location in space where the sun had been. Within years, The point where the sun had orbited the galactic center would be indistinguishable from the surrounding interstellar medium, because the solar wind that had once pushed back the interstellar gas and dust, creating a bubble called the heliosphere that extended approximately 100 astronomical units from the sun, would no longer exist. The interstellar medium, the thin gas and dust that permeates the space between stars, would slowly flow back into the former heliosphere, filling the region with the diffuse hydrogen and helium, and trace heavier elements that characterize the local interstellar neighborhood. The precise location in the galaxy that had been the center of our solar system, the place from which all human astronomy had been conducted, and from which the universe had been observed for the entire span of human civilization, would become simply a point in space with no distinguishing characteristics whatsoever, indistinguishable from any other point in the interstellar void. The address of humanity erased from the cosmos as completely and as quickly as a footprint in the sand when the tide comes in. The cosmic background radiation that permeates all of space, a faint glow of microwave radiation left over from the Big Bang approximately 380,000 years after the universe began, would be the dominant electromagnetic radiation experienced by a frozen Earth drifting through interstellar space, just as it is the dominant radiation experienced by any point in the universe that is far from any stellar source. This radiation has a temperature equivalent of approximately 2.725 Kelvin, just above absolute zero, and it fills space uniformly in all directions, a reminder of the universe's own thermal history, its own transition from a hot, dense state to the cold, dark, expanded cosmos we inhabit. A frozen Earth drifting through the interstellar medium would be bathed in this ancient radiation along with the light of distant galaxies, the radio emissions of pulsars, and the occasional cosmic ray particle, a tiny frozen world in a cosmos that is mostly empty and mostly cold and mostly dark, and yet also threaded through with the ancient light of the Big Bang itself, a universe still glowing faintly from its own birth, still warm enough to be measured, still carrying the memory of when everything began in a single moment of unimaginable heat and light. The timescale over which Earth's radioactive interior heat would be exhausted stretches far beyond the current age of the universe. The primary radioactive heat sources in Earth's interior are isotopes of uranium, thorium, and potassium, specifically uranium-238 with a half-life of approximately 4.47 billion years, uranium-235 with a half-life of approximately 703 million years, thorium-232 with a half-life of approximately 14.05 billion years, and potassium-40 with a half-life of approximately 1.25 billion years. These isotopes will continue to decay and release heat deep within the Earth for billions of years into the future, declining slowly as the radioactive parent materials are consumed by their decay chains, but providing a continuous, if diminishing, heat source that will maintain some level of geological activity, including plate tectonics and volcanism, for billions of years. The frozen Earth drifting through interstellar space would therefore not be a geologically dead world for an immense span of time, its interior still slowly convecting, its core still partially liquid, its mantle still capable of generating the volcanic and tectonic activity that has shaped its surface since its formation. All of this happening invisibly beneath a frozen surface that receives no light from any star, the planet alive in its interior and dead at its surface. warm in its deepest places and cold beyond measure at its face. The question of what would happen to time on a sunless Earth, not physical time as measured by atomic clocks, but experienced time, the sense of duration that all living things and especially humans use to organize their existence, would be one of the most disorienting aspects of the scenario for any surviving human beings. All of our temporal frameworks, the day divided by the movement of the sun across the sky, the year defined by the Earth's orbit around the sun, the season determined by the changing angle of solar illumination, would become meaningless simultaneously. The Earth would still rotate, and a technical day of 24 hours would still elapse with each rotation, but there would be no observable difference between any rotation and any other. No dawn, no dusk, no noon, no midnight defined by light, only the unchanging dark interrupted by stars that moved slowly across the sky as the planet turned. The human circadian clock, freed from the light entrainment that normally keeps it synchronized to the solar day, would drift on its own intrinsic period of approximately 24.2 hours, meaning that without artificial light cues, human sleep and waking cycles would slowly shift relative to any externally defined time, the internal clocks of the survivors each drifting at their own pace, communities gradually losing synchrony with each other. The shared experience of time dissolving along with everything else that the sun had made common to all of humanity. The philosophical implications of the scenario we have been exploring all night lead inevitably to a consideration of what the sun has meant, not just physically, but existentially, to every civilization that has ever existed on Earth. Every major religion, every mythological tradition, every ancient cosmology has placed the sun at or near the center of its understanding of the world. The Egyptian Ra, the Greek Helios and Apollo, the Aztec Tanatia, the Hindu Surya, the Japanese Amaterasu, the Inca Inti, all were deifications of the same physical reality, the burning ball of plasma that made everything possible, that grew the crops and warmed the skin and lit the path and marked the passage of time and gave the world its colors. The sun has been worshipped not because human beings were naive, but because they were perceptive, because they understood at a level deeper than formal science that everything they valued, every meal they ate, every warm morning they experienced, every child they watched grow up in the light, was a gift of that star, a loan of energy that had been extended to their planet for 4.5 billion years without interruption, and that, in the normal course of stellar evolution, would be extended for several billion more. The permanence of the sun was the foundation of every assumption human civilization had ever made, and the thought experiment of its disappearance is so disturbing precisely because it reveals, in the starkest possible terms, how absolutely everything depends on something we have never had to think about protecting. The universe itself, in the billions of years after the sun's hypothetical disappearance, would continue its own vast and indifferent evolution. Stars would continue to form in molecular clouds where gravity overcame the pressure of gas and radiation, hydrogen and helium contracting into new fusion reactors that would shine for millions or billions of years, and then die in ways determined by their mass, either swelling into red giants and shedding their outer layers as planetary nebulae before collapsing into white dwarfs, or accumulating enough mass to end in spectacular supernova explosions that seeded the surrounding space with heavy elements, the raw material for new planets and new chemistry. Some of those new planets would orbit in the habitable zones of their stars, and some of those planets might develop the chemical complexity that leads to life, and some of that life might develop the cognitive complexity that leads to astronomy, and some of those astronomers might one day detect a rogue planet drifting through their stellar neighborhood, a dark world of approximately the right size and composition to have once supported liquid water, and they might wonder what had happened to it. And they might not know that they were looking at the former home of the only technological civilization that the universe had produced in this corner of the galaxy, drifting frozen and silent through the dark, all its libraries and all its music and all its genetic diversity preserved in ice, a message in a bottle that no one had sent and no one would read. Moving at 29.78 kilometers per second toward no particular destination in a universe that was under no obligation to notice. The stars themselves, observed from the frozen surface of a drifting Earth over thousands and millions of years, would slowly change their apparent positions as Earth's trajectory carried it through new regions of interstellar space, the familiar constellations gradually distorting as nearby stars moved relative to the background of more distant ones, and as Earth's own motion carried it away from the vantage point from which human astronomers had named and cataloged those patterns. The constellations are not fixed physical structures but perspective effects, the result of seeing certain groups of stars from a particular location in space. And as Earth moved to a new location, the perspective would change, and the constellations would dissolve into new, unnamed configurations that no human eye would ever see. Orion would lose his belt. The Big Dipper would no longer hold its familiar shape. The Southern Cross would cross into new orientations. Over millions of years, every star pattern that had guided sailors, inspired poets, organized calendars, and given names to the gods would become unrecognizable. The sky rewritten by the simple fact of movement, the universe rearranging its familiar face into something new for an audience of frozen molecules that could no longer look up to see it. The greatest light show in the history of the planet performing to an empty house for the rest of time. And here we arrive at the 100th and final fact of tonight's journey, a fact that is less a piece of scientific data than a recognition, an understanding that contains all the others within it. The Sun, that ordinary middle-aged yellow dwarf star in the outer arm of the Milky Way galaxy, is not remarkable in the cosmos. There are approximately 200 to 400 billion stars in the Milky Way alone, and an estimated 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars, making the total number of stars in the observable universe somewhere in the range of 10 to the 24th power, a number so large it has no useful analogy in human experience. Among all those stars, our Sun is in every measurable physical way completely average. Its temperature, its mass, its luminosity, its age all falling close to the middle of the distributions for stars of its type. What makes the Sun extraordinary is not what it is, but what happened around it, specifically that on one of its 8 planets, at a distance from the Sun that happened to place that planet in the liquid water zone, a chain of chemical reactions began approximately 3.8 billion years ago that eventually produced, through an unbroken sequence of chance and selection that has never been fully interrupted since, the remarkable accident of life. And then the even more remarkable accident of minds that could look up at their star and ask what would happen if it disappeared, and then lie down in the dark and listen to the answer, and find that the answer, for all its strangeness and its cold, was somehow also beautiful. Let these final facts dissolve now, like the last light of a star crossing the room. You have traveled far tonight, from the first lightless second to the deep, cold silence of interstellar space, and your mind has held it all with an ease that surprised you, because the science was always just a vehicle, a quiet river carrying you somewhere warm and still. The constellations are rearranging themselves behind your closed eyes. The frozen ocean is somewhere very far away. The tardigrades are sleeping in their ice, and the universe is continuing its patient business of stars and galaxies and dark matter and time. You do not need to carry any of this with you into sleep. It will all be here when you return, the science unchanged, the universe still vast, the questions still beautiful. Simply let the last number fade and the last molecule and the last frozen world drifting through the dark and feel only this: the warmth of where you are, the weight of your body, the slow and easy rhythm of your own breathing, which is itself a gift of a star that is still burning, still there, still 8 minutes and 20 seconds away, still sending its ancient light toward you even now. Thank you for spending this night with Learn When You Sleep. You came here with a curious mind and a willingness to let science be something restful, something that washes over you rather than demands from you. And that is exactly what it was meant to be. The universe we explored tonight is the same universe you live in, and it is stranger and more generous and more fragile and more enduring than any single journey through it can capture. Every fact we visited was a doorway, and behind every doorway were 1,000 more. And that is the nature of science. It never runs out of room. It never stops being astonishing. And it is always here for you, in whatever quiet hour you need it. Sleep well now. Let the stars do their slow work above you. Let the planet carry you through the night at its ancient speed. Let everything you heard tonight settle into the deep and patient part of you that knows how to hold large things gently. This has been Learn When You Sleep. Good night.